Welcome. In this lecture, we shall study the shear stress distribution for circular sections of beams. Let's draw a circular cross section with radius r. We show an arbitrary layer defined by a thin strip of thickness del y at a distance of y from the neutral axis. The width of the arbitrary layer is 2 times the square root of r square minus y square from the Pythagoras theorem. Starting with the general shear stress formula, the moment of area can be written in the form of an integral equal to the width of arbitrary layer times del y times y with the limits from y to r. The shear stress is equal to S over Bi times the integral of 2 times the square root of r square minus y square times del y times y. Twice S over Bi can be taken outside the integral as they are constants. We can substitute r square minus y square as p square to simplify our calculations of the integral parameters. We hence get the value of the shear stress as 2 over 3 times S over Bi times r square minus y square to the power of 3 over 2. As we know the width b as 2 times the square root of r square minus y square, the shear stress is simplified as S over 3I times r square minus y square. This equation shows that the shear stress is a function of y of order 2, meaning that the curve is parabolic. The double derivative of shear stress as a function of y is found to be negative in sign. Hence, the curve obtained is of maxima type with respect to zero shear stress line. To find the maximum shear stress, we take the first derivative of shear stress with respect to y and equate it to 0. We get the value of y as 0. Inserting this value in the shear stress formula, the maximum shear stress is found to be 4 over 3 times S over pi r square. Since average shear stress is given by S over area, which is pi r square, hence the maximum shear stress acting on the neutral surface is 4 over 3 times the average shear stress acting on the transverse or cross section of the beam. We plot the distribution of the shear stress in the form of a diagram alongside the beam cross section and label the same. If, for example, we assign the radius of the cross section of the beam as 50 millimeters and the maximum shear force as 100 kilonewtons, then the maximum shear stress is found to be 16.97 megapascals. In the next lecture, we shall study the shear stress distribution for triangular sections of beams.